Hello there, everyone. This is Bilal Mushtaq, CWID 50355932. And this is my presentation for the 595 research project. Let me start sharing my screen. I'm going to now open up the presentation. And let me start with the slideshow. So the name of the project is VRSMY9, Vehicle Recognition and Speed Monitoring System using YOLO V9. And as you can see my name over there. So basically, let's talk about the problem. Now, NHTSA, which is basically the authority that um, surveys and takes care of, the highway traffic in the United States. It reports that 18,270 people lost their lives in car crash during the first half of the year 2024 in the United States. So that's an alarming number. Like almost 20,000 people losing their lives for a common cause. That is something to be, you know, something that needs to be taken care of. Almost one third of total roadside fatalities in the US, they occur due to speed-related accidents and crashes. Now, the existing systems that are like in practice already, either they're computationally like very expensive, like they require a lot of processing power, or they're very slow in detecting overspeeding vehicles. In both the cases, they're not practically applicable in modern day applications, like in, traffic scenarios and where, vehicles and speed, can be detected and, systems that are not powerful enough, should be able to like support it. So that's basically where the problem is. Even though a lot of work has been done in it, but at the end of the day, if it's not practically applicable, if it's not accurate enough or not, fast enough, then it cannot be used. So, and there are some issues like bad weather, varying lighting conditions, and complex traffic scenarios that make it a challenging task. Now, I'm gonna, talk about a few of the techniques that are already used. There are plenty of techniques, but these are the most, you can say, effective ones among all of them, which includes like the most, you can say, old school traditional blob analysis. It is cost effective compared to traditional methods, but it's not effective enough in the challenging weather conditions. Harlake feature classification, it produces better detection results in complex traffic scenarios because of, the Harlake features. They're able to like detect vehicles in different shapes and sizes and, in different positions and even in overlapping conditions. But the problem is they aren't robust enough to be able to operate in low lightning conditions. Convolutional neural network, the infamous method, is effective than the traditional methods when handling various vehicle shapes and sizes, but the classification accuracy comparatively is lower when it comes to complex traffic scenarios. 3D modeling and 3D bounding boxes. This is what one of the famous techniques that is being used by a lot of um, re- in a lot of research by scholars. It is very accurate in effect, in distinguishing between vehicles that closely they look like each other, So because of the 3D model itself, they're able to like distinguish between the shapes and the models. And but the problem with it is it's not scalable. When you work with large data sets, it gives you scalability issues. And finally, data augmentation, in which if you have small training samples, you can like perform data augmentation procedures like rotation and flipping and all that kind of stuff. And it produces more training samples for you. So with limited training data, data augmentation is a go-to technique. But if you have a large data set, which you do in most of the cases, it starts overfit. So in all, you have some kind of trade-off, and like that is why the problem still exists. What we are suggesting or we are proposing like I basically am proposing, is VRSMY9, as you already know. It is based on YOLO V9, a latest novel object detection model, and backed with the easy OCR framework. Now YOLO basically, I'll get to in the next slides I'll explain more about both of them. So like the model is our system is based on these two. Now the VRSMY9 can detect multiple vehicles simultaneously in a single frame. So if there are many vehicles in a frame, it is able to detect all of them. So that's one of the features that it has. Furthermore, there's speed estimation that is also being done for every vehicle that is moving within that frame, so that we can determine which vehicle is within the speed limit and which is overspeeding. Every overspeeding vehicle passes through the license plate detection. Now, the vehicles that are already within the speed limit, they are let go of. They're not, moving to the next phase of, license plate detection, but the vehicles that are, going beyond the speed limit, their license plates are detected, and then the contents of the license plates are also, extracted. So the next point says the same thing. So what it does is, in this project, since we're talking about, mapping onto practical applications, so all that data extracted from, these overspeeding vehicles is, saved in a folder so that a record can be kept of, which vehicle, was moving fast and, which vehicle was, moving slow. Um, like was within the speed limit. And then the part about using YOLO V9 is it doesn't have as many parameters compared to the rest of, the deep learning networks. So like we're using YOLO V9T model. So it has like 2 million parameters. So it makes it lightweight. And I'm going to show you, I have, um, even though the training was done on a GPU, I have the execution for a GPU and a simple laptop that I'm using right now, which is just a Core i7. It doesn't even have like a GPU or an NVIDIA graphics card, but I'll show you that it runs on both of them. That is basically what we wanted to show, a model that can be, supported by all kinds of machines, and it produces faster detection. So this is the basic architecture in which, the input video stream. Of course, we don't have a live video right now, so what we're going to use is, we're going to use a dataset video, which is hard coded in the program, but you can always use a live stream video as well. So the initial step would be the vehicles would be detected using YOLO V9, and every single one of those vehicles will pass through the speed estimation process. Um, Once the speed is determined, if it's going to be compared with the threshold, of course. In our program, just for simplicity's sake, we've kept it 10 mph. So if the speed is above 10 mph, then it's considered as overspeeding, and then it passes through the next steps, which is license plate detection using YOLO V9. So, license plate is detected first, and then the features of the license plate is extracted. If it doesn't have, like, if it's not traveling with a speed which is above 10 mph, in this case, you can like change that factor. Um, then, it won't go through the license plate detection and the next steps. Now, YOLO V9, again, this is just to give you an idea of how it is different from, relevant architectures. So we have like it's an adversarial network. We have reverse um, call. We have deep supervision, and we have programmable gradient information, which is a novel technique architecture that is used in YOLO V9. And as you can see that, it has prediction head, auxiliary branch, and main branch. So it's like divided. So that's why information retrieval within this network is like more strengthened compared to the rest, and that makes it use lesser bit of parameters and still save the information. Like there are lesser losses compared to the rest of the architectures. Um, it it contains around 2 million parameters. I'm talking about the most simplest model. Of course, it has deeper models as well, but again, in this application, the essence of it was to keep it as lightweight as possible. So this lightweight model boasts a high detection accuracy as well. We'll go to the results in a moment. And the other is the Easy OCR framework. So the Easy OCR framework, as you can see in the name over here, it has like this entire framework in which, initially when an image comes in, it like the image can be extracted from a video as well, of course. So this craft is a deep learning basically model that detect areas within an image. And wherever it sees like a text, it produces bounding boxes around that area so that, it knows like what where, we have like the numbers or the letters, etc., etc. And then it passes through the mid process where, the text regions, they are further refined. They're refined so that, text recognition can be, carried out. And then the greedy decoder, again, and of course, it passes with the ResNet and the LSTM model, all of those models that basically produce the recognition. And then the greedy decoder, what it does is it interprets those models' predictions to produce readable text. So, the heavyweight models between the ResNet, the long short term memory, and the CDC, they basically carry out the recognition. Of course, this is again what we have used. It can be changed as well depending on application. And then of course it produces the output. So we're going to see the live application of it as well. So let's briefly discuss all the kinds of tools and libraries that we've used. We're using Python programming language version 3.10, Anaconda Python distribution, Jupyter Notebook, Ultralytics YOLO VNAND library. This is where all the functions and the methods of YOLO V9 are present, and then Easy OCR library as well. So we'll take a deep dive into everything. Now, I want you to have a look at this particular, set of images over here. So during training, you can see that, the model was able to like, produce, the correct labels for the bounding boxes. For instance, you can see it says license, license, and all of these different aspects, even though these are the data set that we've used contains a diverse set of pictures. You can see some of the pictures are like, in Arabic over here, and then, from different parts of the countries. And again, in different varying angles, different lighting conditions. The reason was we wanted to make it robust enough and trained enough that it can, like work with, different kind of scenarios. So, it produced all those kind of labels. And these are labels with confidence scores. So, this basically tells that how confident, how sure the model is of, like detecting that it's a license plate. Now, as you can see, zero point 0.9 score is better than zero point 0.5. So just to give you an example. So as you can see that, not only is it producing labels, it is like giving you an idea of a confidence score of, for instance, look at this part right here. It's not as sure that, whether it's a license plate or not right here, even though it is, but actually I'm not sure whether yeah, it is, I think. But still, it's the confidence score tells you the story. Moving on. This is a very important picture right here. I want you to have a look at it first. As you can see, after the training and validation, the results that we had, they show that the training metrics, they show basically that there is consistent improvement, if you can see over here, right? Because we trained the data set, the entire model on, 1,000 epochs. So as the epochs, progressed, the losses, they started to decrease. Whether it's the box loss, the classification loss, all these losses, started to decrease. Same goes with validation. So that basically shows that this model with as the data as the epochs progressed, it produced lesser and lesser bit of losses. And it also, you can also see the precision scores over here, and the MAP metrics as well, which show that I'll also show you the confusion metrics in the in the next slide. So basically what it shows that the score between 0.75 to 0.95, as we can see over here, is a high, a high score. And this is basically a precision score. So this means that it avoids false positives, which is very, very important, for any model to do. Um, and that's one of the, a great result that we got. But we would want the recall to be a bit more better. It's between zero point 0.6 to zero point 0.8. So it does miss a few of the, detections that it was supposed to detect, but it wasn't like it missed for some reasons. It's a decent score. I won't say it's bad, but we would have liked it to be even better. And these metrics, the MAP to 50 and for 50 to 95. Now, this is basically the general or, the simpler parts of the data where you can say that it's the parts where the mean average precision uh, is at 50% IOU. And that means that this area was not as difficult to detect compared to, the more difficult part of the data. So over here, you can see the scores were between 0.65 to 0.85, um, in which you can say that this is like acceptable. This is a good score. But as you moved from 50 to 95, like, the complex part of the data, it dipped down to 0.25 to zero point 0.4. And this was something that, we would have liked to be better. But, in future works, we would definitely, try our level best to, work with techniques or different some tweakings need to be done, I believe, in the future works that would improve the score. So a bit more about the performance metrics, the precision 0.75 to 0.95, it shows that the model is highly accurate in avoiding false positives, meaning that if it predicts a detection, it is correct most of the time. So a great signal. Recall 0.6 to zero point 0.8, the system moderately captures true positives. It misses some detections. MAP at 50, zero point 0.7 to 0.85 represents strong overall detection accuracy at a commonly used IOU threshold, which is like 50%. But MAP at 50 to 95, which is 0.25 to zero point 0.4, the score, highlights stricter evaluation across multiple IOU thresholds where the system's performance drops, suggesting challenges in precise localization and handling difficult cases. So we've already talked about it. Now this is the part I'm going to show you the slide and I'm going to show you in real time as well. So this is the real time testing. Let me first show you through the slides and then I'm going to show you the videos as well. So as you can see, this is basically the real time experimentation of the program itself. So when we ran the program, whenever there were cars in the frame, doesn't matter, one car, two car, or more than two, it drew the bounding boxes and detected the vehicles over there. As you can see, the two cars parked on the left are detected, and this moving car is detected as well. And its speed, since it's 8.8 miles per hour, it was correctly estimated. And you can see the green color, which tells you that it's acceptable and it doesn't move on to the next step. Here, I also want to tell you how we're doing the speed estimation. So it's a very basic, simple technique in which we're using the Euclidean distance, like a distance between point A to point B. So in the code, I'll show you that, we have like marked two coordinates where, the distance between those two coordinates is 6 meters. So any vehicle that is moving from that point A to point B, how much time it's taking to reach between those 2 points is basically, divided. So speed divided by time, you get, sorry, distance divided by time, you get the speed. So that 6 meters is divided and then it's converted into mph. I'll show you in the code as well. Again, we also learned that this technique, even though it's simple in computer vision tasks, it works, but it's not as effective and robust as you would want it to be. More about it in the next slides as well. So now this is a real-time testing of a vehicle that is overspeeding. It's 11.6, and in our case, 10 mph is basically, the speed limit. So since it's going above 11.6, mph, you can see that. I'll show you how this license plate is popping up on top of the screen. It's being extracted. So after the detection of the vehicle, since its speed was above 10, this license plate was extracted and then its contents were saved. I'll show you the entire process, after the presentation. So you can see that it's displayed in red color, showcasing that, it's above the speed limit. And moving on, another example of the same case, another car, but 24 miles per hour. So, again, another or speeding vehicles example. Now, let's talk about the challenges once again. The biggest challenge that we came across, of course, which is like understandable as well, was finding the right data with enough images that weren't distorted and had visible license plates. So we found a lot of data to work with, but either, the images were like distorted, or, the license plate wasn't visible enough, or, it was a very blurry and messy kind of resolution. In all those kind of cases, like if the data is not clean, if it's not workable, then there is no point of moving on to the pre-processing, the training, and all that kind of stuff. So we had to like I particularly had to like work hard to find the right data. And Speed estimation powered by computer vision isn't as effective compared to utilizing radar sensors for estimating, speeds. I'll also show you here for, because I was talking about the data. I'll show you the data set that I used. Let me see. Let me see. Maybe I've kept it here somewhere. So I'll show you the data set as well. I've also put in a reference in the report as well. Um, yes, so the speed estimation, just a moment. Yes. Yes, so the speed estimation powered by computer vision isn't as effective compared to utilizing radar sensors for estimating speeds. So this is what we learned the hard way. After, the project was completed, I realized, I also went through some papers, and it made me realize that, there's a reason why people use radar sensors for calculating speed and not, the cameras in computer vision. But then again, it was good enough for this particular project, but down the road, if I would ever wanna, use speed estimation, calculate speed, I'll use radar sensors. And then the model didn't showcase a high enough accuracy as we would have liked when handling difficult cases, such as overlapping vehicle images and unclear license plates. The difficult cases, the unclear traffic scenarios in that kind of situation, the model still needs work. Um, and in conclusion, I would say that this system is a real-time vehicle detection and speed estimation system, which is lightweight and accurate enough to be implemented on devices that might not have powerful GPU at their disposal. Um, Now, it is trained on a data set containing diverse set of vehicle images that had varying angles, different weather and lighting conditions, and, many different license plate designs, and we trained it for 1,000 epochs. Highly accurate in avoiding false positives, but miss some valid detections. And detection accuracy is impressive in general cases, but the performance drops a bit when handling difficult cases. We've talked about it already. So, these were some takeaways from the project overall. And as far as future work goes, this framework most definitely it serves as an important stepping stone for not only for us, but for anyone else who wants to do further research in the fields of autonomous vehicles, unmanned aerial vehicles, intelligent transportation systems, robotics, intelligent AI agents, domestic security, even healthcare, anywhere where you feel like, you want a smart embedded device for any matter, and you want it to even not be like computationally expensive, not be not have a lot of computation power, but still it should be able to um you know carry out the detection and carry out the tasks. So this is an important research in that aspect. Applications that are computationally inexpensive systems are to be built without compromising on accuracy and performance. So this is, like I said, any application where you want the system to be, supportive of, the device constraints. In those kind of scenarios, this is an important project, and further research can be done, and this project can, serve as a stepping stone in that matter. These are some of the references um, for, the different um, contents. Now let's move on to the application. First, I wanted to show you when I carried out the training and, produced the results on the GPU, how it looked like. I don't have the access to the GPU right now, but I wanted to show you. So this is basically the code. When I ran it, it'll show you. So as you can see, it has 27, 26 FPS. As you saw, the car was moving on, and the speed was there. And that slight pause, kind of what you feel is where that extraction is happening. Same thing over here. All these cars. Now this is the GPU, and uh, actually there was another part of it that I wanted to show you. Even in that case, there all of the images are being saved in a folder. Like as you can see here, this is a folder where all the extracted images automatically they save in. I'll show you a practical example right now. So let me open up my Conda prompt. Conda activate. This is my model name. I'm in the environment. This is the folder. And here I'll open the notebook. So, yes, this is basically the folder, and this is the notebook. You see this folder right here? This is empty right now. I wanted to show you that it's empty. And now let me show you the code a bit. As you can see, the library is important, Ultralytics and YOLO. And these are a few flags over here for the purpose of um, controlling the flow of the program. I believe the recording is going to end soon on Zoom, so I'm going to make it fast. So um, the model that I'm using is .pt, not .engine. On the CPU, on the GPU, I used the .engine files, but on .pt, it's not heavy enough, so it's easier to use on devices that are simpler and don't have a lot of computational power. These are the three lines I was talking about that we virtually basically automatically draw in every frame through which, the vehicle is passing on. And this is where how it is converting into, as you can see, if the vehicle passes through the line one, so, it is detected when it's detected and it passes through the line two. So, the difference um, of the time is basically like the difference of the time is basically divided by the like distance is divided by the time, and then it's going to multiply by 2.24. So this is how it converts into mph, and this is how speed estimation is being done. And again, these different conditions, I'll show you the program by running it and explain it to you how it's running. So run kernel, restore kernel, run all cells. Now, the main difference that you feel in the video before and the video, like the execution now, is basically the frame per seconds. Let me show you. As you can see, it is moving slowly this time around. You can see the number of seconds. You can see the frame per seconds over here, 8, 9. In the GPU, those were 25, 26. So even though the detection is working properly, this system that I have right now this laptop is very computationally inexpensive. It doesn't have a GPU at all, but still it's able to host it. You can see that, it's detecting the speed 9.1 mph. And now I want you to pay attention on this one right here. As you see this car moving on, it's going to detect it first and see 11.6. So, it took out that extraction. I showed you that folder which was empty. Let's see um, what's going to happen to that folder once this video is over. So one car went through with that speed, 24 miles per hour. And, same thing happened over here. 14 miles per hour. It got covered a bit. The label was there, but it wasn't. Okay, so here the video ends. As soon as it ends, I'm gonna go to the this folder right here, and as you can see, every single image over here. Let me also tell you how this image is. You see the R606L. R6, instead of 6, it says G. So this is a bit of an inaccuracy from the system, but this is how the convention is. And this, let me show you one more thing that I wanted to, an example of another image. See this one right here, E67OS, E67OS. Even A is, identified perfectly. The letter before that is, we're not considering that one because it's not an English alphabet. And then another one, let's take this example over here. So as we can see, 3K96, 3K96, and it also does this properly. So this is how it is extracting the images and then placing them in a folder. And the entire code is also, don't have much time left, but I'll just show you. So the different functions defined for the lines, and then these are um, there are many if conditions where you basically depending on where the vehicle is. So as it passes on from one frame, like from one point to another, um, you go to the next steps, and this is where the snaps are taken, and they are saved into this folder right here, overspeed record. And you can also see the names of the license plates over here of every single vehicle that passed through. So I believe that concludes the project, and as fast as I could within the specified time period, uh, the the presentation and the execution of the code. Please let me know if you have any questions. I would be more than happy to answer you. Thank you so much once again.